Okay, this is day 2 of polar graphing, and today we're going to cover conic sections, circles, lines. Okay, the first, and this is all in the reading section 5.2, and you should read this. Read and study, that'll be part of your homework assignment. Read and study section 5.2, and the rest of it that we didn't do before, pages 566 to 568. That runs you through the end of the section. Okay, and the first thing you're going to encounter is conic sections, and they give you a couple of examples of graphs of conic sections, and this equation is given. R is equal to K divided by A plus B cosine theta, or R is equal to K over A plus B sine theta. And this information is also given, and bear with me, I'm just going to write that. I should have written this down ahead of time, but I guess I didn't, so you're going to have to bear with me. All right, this K thing is given as AEP, and I'll explain what that is in a second. Well, A is this number, E is eccentricity, and P is something else. We'll get to that. Now, if these values down here, if this number is bigger than that, and they do use absolute values, and I'll tell you about that in a second, you have an ellipse. If A is bigger than B, that's a hyperbola. Or you could say if B is less than A. Okay, if they're equal, that's a parabola. And the reason that these absolute value signs are used, because this is the definition of how this works. The focus is at the pole, and what you're going to have is an ellipse in certain cases is going to sort of look like this. But that ellipse could actually look like this. And that's going to be a difference as to whether this thing's positive or negative, whether it does that. Now, for a sine, the ellipse wouldn't open this way. It would sort of open up or open down. And that could be that negative sign right there. It could be positive or negative. So by varying the cosine and the sine, you'll get ellipses that go up and down versus left or right, or hyperbolas even that go left and right, up and down. Now, I would encourage you to, when you're practicing this stuff, put it into the graph or change these values, change that sign, change the cosine and sine, and see what happens. Experiment with it. That's why all these absolute values are given. Okay, now this distance P is defined. If you take a look, there's the focus, and remember, we talked about focus directrix definition. P was, in this context, is defined as the distance between the directrix and the focus. Now, in general, during the year, you know that I didn't like to just throw equations out there and say, yep, here it is. We like to see where this stuff comes from, and it's really not that complicated as to where it comes from. You will understand this because we've done it. We know this stuff. All right, so we're gonna go through the background on this because it doesn't even take all that long. Okay, so I'm gonna sort of start with an elliptical look here. Now, for an ellipse, of course, on this perpendicular from the directrix to the focus, it's going to be a little closer to the focus because D2 being ED1, D2 is going to be a little less than D1 because eccentricity is less than 1. All right, so we're going to have an ellipse that sort of opens like so. But even if it was a parabola, it would open in a similar fashion, or a hyperbola, but just not as rapidly. Okay, let's call this a variable point r theta. Now, if the focus is at the pole, that simplifies some of the analysis here fairly easily. There is D2. It's the distance from the pole to a point on that, which is R. Okay, now if I draw this, that's D1. Now, D1 is a summation in this diagram of this distance plus this distance. Now, if I take a little look at this right triangle right here, that distance is this length times the cosine of theta. That length is r, so this is r cosine theta. All right, remember that D2 is equal to E D1. Well, D2 here is nothing more than r. D1 is P plus r cosine theta. distributing, r is equal to EP plus ER cosine theta. Now the goal here is to isolate this for r. That's done by subtracting ER cosine theta from both sides, factoring the 1 minus E cosine theta is equal to EP, and then dividing both sides by this expression here, EP over 1 minus E cosine theta. Now this sort of looks like what we had up here, and it can be easily transformed into AEP, K being AEP, and then by multiplying top and bottom by A, then I got AEP, and then I have A minus EA. Let's do that. Multiply by A over A, which is 1, not changing anything. R is equal to AEP over A minus EA cosine theta. Okay, one thing I forgot to mention up here, and this was given, is that they say that E is equal to the absolute value of B over A. Well, that can be seen here. Is this B that they were talking about in here is equal to EA. All right, so these two things really aren't any different, and this is exactly where it comes from. Okay, well, let's take a look at an example here. And this is number... Well, there's an example of a hyperbola in the book. Okay, so we'll take a look at the example from the book that is the ellipse. All right, and I'm going to do this on the graph paper. I think I have it. I thought I made myself a blank graph paper. There it is. So, all right, number 18 out of the book. And for homework tonight, you want to do this. You'll have one of these problems, number 17, which is a hyperbola that you'll do. Okay, number 17, it says R is equal to 10 over 3 plus 2 sine theta. Okay, so that sort of fits the definition that we've just been talking about. Well, let's make a little table of, well, here, let's get your auxiliary graph. This is a period of 360. All right, so theta r. We'll just do the major values here. Okay, so when theta is equal to 0, sine theta is 0. So this is 10/3. When theta is equal to 90, sine theta is 1. So 10 divided by 5 is 2. When theta is equal to 180 degrees, sine theta is back to 0. So this is 0. So 10/3. When theta is equal to 270, well, that is when this is at its low point. That's -1. 2 times -1 is -2. 10 over 1, in this case, is 10. All right, so we have, if we use 1 ring as 2 units, 10/3 is a little over 3. Okay, 2 right there. 10/3 here, and we're down here. Okay, so if you accurately sketch, you get, something that looks like this, which is an ellipse. Okay. Now the question says, what is the transform this into its Cartesian equivalent? All right. I should have done this before, but I'll move back to it. Okay, recall from yesterday that you'll remember that the polar axis system looks like this. There's the pole and the axis. Here's a point r theta. Well, if I sort of transpose the Cartesian coordinate system on here, I can set up a little right triangle here, and this is r, here's x, and here's y. That's a simple relationship. X is equal to r cosine theta, and y is equal to r sine theta. And r squared is equal to x squared plus y squared. All right, we'll keep that in mind. And those three things as we transform this. Okay, so if I start with r is equal to 10 divided by 3 plus 2 sine theta. Cross multiplying this, I get 3r is equal to, or 3r, pardon me, plus 2r sine theta is equal to 10. Now r is the square root of x squared plus y squared, because r squared was, from my last piece of paper here, r squared is equal to x squared plus y squared. R sine theta is y. Okay, now this is now a Cartesian equation. The question is, how do I get it into a form that I know what it looks like? All right, well, it's not as hard as it looks. Okay, now I'm going to move, this is done in a book, the 2y to the other side. And the reason I'm going to do this is I want to square this radical out of here. But if I square it as is, I square this binomial and I still have radicals. So if I isolate the radical and then square, I get rid of the radical. All right, squaring this side, I get 9 times the quantity of x squared plus y squared. Over here, squaring that binomial, that's 100 minus twice the product of these two things, minus 40y plus 4y squared. Distributing 9x squared plus 9y squared is equal to 100 minus 40y plus 4y squared. Okay, exercise left to the student. And we have done this before. I can get it into general form and into center radius form, okay? And in center and radius form, it looks like this. X over the square root of 20, quantity squared, plus y plus 4 over 6, quantity squared, is equal to 1. All right, well, let's check and see if this holds up as to what we see here. All right, the center of this, just glancing at it, is at 0, negative 4. All right, well, here is 0, negative 4 right there. Okay, that's halfway between here and here. Okay, that checks out. Okay, 6, major axis, major radius, I should say. Distance between here and here, or here and here, exactly. Okay, now the focal distance, so I can say that A is equal to 6, and C is going to be equal to 4, because that's the distance between the focus and the center. Well, by the Pythagorean relationship, a squared is equal to b squared plus c squared, so b must be equal to the square root of 36 minus 16, which is the square root of 20, which you will get if you go through this process. Remember, exercise left to the student. Okay, now when you do your homework tonight, you'll do a hyperbola. And I do, oh, maybe I should, let's check by graph and see if we did this correctly. Okay, so I'm going to have 10 divided by 3 plus 2 sine theta. Okay, and I will graph. Now, I don't quite get very much there because my window isn't doing it for me. This is something that was left over from yesterday. Okay, I need to go 0 to 360 to get this whole thing. And there is that ellipse that we had just plotted, and everything checks out. Okay. All right, you read and study about those conic sections, and you also do problem number 17. Let me see here. I need another piece of paper. because we're going to talk about some of the specialized equations in polar coordinates. All right, this is special cases, special equations, let's say. All right, there's this one. R is equal to, say, 5. What do you think that looks like? Simple circle. Okay, so R is equal to a constant. It's going to be a circle, and that's about as easy as it gets. It doesn't matter what the value of theta is. Keep in mind that if I graph y is equal to 10, that's just a horizontal line because, the y values never change. Well, it's the same principle here. R never changes. R is always the same number regardless of the angle. Okay, I have something like this. Theta is equal to 30 degrees. Well, I can't graph that on the grapher. The reason I can't graph that on the grapher is because R is written as a function of theta. Okay. Now, we have a similar situation, x is equal to 5. Now, when we try to graph in function mode, we can't graph a vertical line x is equal to 5 because it is a function machine. Well, this thing can't graph theta is equal to 30. That doesn't mean it doesn't exist. It does exist. Okay. All right, well, we have another special case, and if you read and study, you'll see this. Okay, if I have something like this, 10 cosine theta. Now, yesterday we had 10 cosine 3 theta. This is going to be quite different. Okay, that is a circle with, right, I'm going to draw that because that doesn't even exist. Okay, here's the polar axis. Let's say this is the point 10, 0. Okay. This is a circle. Okay, now here's why it's a circle. Pick a point r theta on there. Here's r. Okay, that is r, and here's theta. Well, if I draw this segment in, you all know that that's going to be a 90-degree angle because this inscribed angle subtends this diameter of the circle. That makes that a right angle. Well, then we have a simple situation here. If that's 10, because there's 10 units here, we have cosine theta is equal to r over 10, or r is equal to 10 cosine theta. If I change this, let's say, to 10 cosine theta minus 30, which will we get? A simple rotation. The diameter is now here. Now, if I put the trace on and type in 30 degrees, okay, r is 10. So that's 0.10 theta. So if you could draw, these are kind of hard to draw really, but I could draw, if I did this, a line through the pole that passes through 1030, and that's where the diameter would be. Now, moving this even a little bit further, I could have 10 minus 90 degrees, or cosine theta minus 90 degrees. All right, so this is r is equal to 10 cosine theta minus 90 degrees. Well, that one is going to look like this. Now, you may recall, and again, you thought you were finished with trigonometry, that cosine of theta minus 90 degrees is equal to sine of theta. All right, so if I replace that, I just have sine, let's just go 10 sine theta. Same thing. By identity. Now, if I put a opposite in front of this thing, it's going to be down instead of up, and I can change that, or I could put a negative here, and it would be down instead of up. Okay. All right. One more special construct, and that is this one. R is equal to, say, 5 secant theta. All right, and this is in the reading as well. Now, this time we're going to have cosine theta raised to the -1 power. Okay, that was 10. Well, 10, what difference does it make? Okay, 10 secant theta. Let's just change that to 10. I didn't change that. Okay. Now, this is a line. Okay, if this is the point 10, 0, pick a variable point or theta on that line. Here's r, there's theta. By basic right triangle trigonometry, again, cosine theta is equal to, now this time, here's the 10, that's the adjacent side, 10 over r. R is equal to 10 divided by cosine theta, which is 10 secant theta. That's in the book. Again, if I rotate this, say 30 degrees, I get still a line, and notice how it plots. It starts here and goes that way and then finishes up because it's coming back from 360. Okay, so that's, now this point right here, if I put the trace on, that is longer than 10, and you should be able to figure out what that distance is. I'll leave that as an exercise to the student. But if I trace out 30, that is where I'm 10 units from the origin. This is 10. Okay, that's perpendicular there. All right, and then again, I could get, say, 10 cosecant theta. Just change that to sine and get rid of this stuff. I get a horizontal line. You can barely see that. Let's make it 5. That way we can actually see. Okay. Again, those are lines. Now there are two ways of graphing lines in polar coordinates. You can have this type of thing here, or you can have this one, which you can't do on the grapher. Okay. All right, so for your homework tonight, here's what you do. Of course, you finish the reading and studying from this section. Okay, and then I want you to do numbers 15 and 16. Now, you don't have to do those on a graph paper because they really don't need it. It's about the lines and the circles of the special cases. And then you do number 17. And that is an ellipse, or pardon me, a hyperbola, and you do sort of what I did here with this. You graph it, and then transform that into center and radius form and general form. Now, by the way, I didn't do this, but you can get these values just by inspection off of that. And you should try to do that too. Look at it and see what you can find out. Well, okay then. I will talk to you tomorrow.